In this lecture, we will continue our discussion regarding ohm meter. Before that, I want to know that assignment one is over. So, I hope all of you must have submitted. So, I also wanted to discuss that assignment one, which you have submitted. So, do you want me to go through those assignments? Let me present my screen. Yeah. So those assignment problems were similar to what we discussed during the lecture one and lecture two. I don't see any difference between them, but still, we should go ahead and again let us practice or let us see what kind of questions were there. Okay. And some doubts were also there regarding some question related to damping. So I hope you were able to solve still. Yeah. So first question was related to PMMC, right? That was common data for 8 sub questions. So PMMC had 100 turns, length of the coil is 1.25 centimeter, and width was 1.5 centimeter. So area would be equal to L into W, right? Air gap flux density was 0.7 Weber per meter square, and a spring constant is 2.25 micronewton meter per degree, isn't it? Resistance is also given 175 ohm. So resistance will be very helpful in that damping questions related to damping. So we needed to, first part was very easy. We needed to find the deflecting torque. So what is the expression? Deflecting torque with current is equal to 4 milliampere, right? So it should be I into B into N into A. So it should be 4 milliampere. So into B 0.7, N is 100. Yeah. And area is nothing but 1.25 into 1.5 into 10 raised to the power minus 4. So we had to provide answer in micronewton meter, right? So how much did you guys got for this question? Could anyone let me know how much did you get for this question? Okay, so let me calculate. I'll calculate it for you. Mm, 4 into 0.7 into 1.25 into 1.5. So it is 52.5 micronewton meter, isn't it? So you must have got this much, 50. Yeah. Yeah. You got this much only? Okay. So let us move on to the next part, that was estimate the sensitivity of the meter. So how to calculate sensitivity of the meter? I discussed in last lecture, right? How to calculate sensitivity. So for calculating the sensitivity, you need to calculate, you know, how much deflection is happening for 1 milliampere current, so that you can calculate, and that should be your sensitivity, right? So sensitive unit of sensitivity is nothing but a degree or deflection per milliampere or ampere, right? So it is also given in the question, right? In question, it is mentioned that you have to provide in degree per milliampere. So I hope you must have provided the correct answer. So do not get confused with, unit. You have to take care of units. It should be degree per milliampere. So it's very easy. So we calculated deflecting torque for 4 milliampere, right? And we need deflecting torque for 1 milliampere. So we will divide deflecting torque by 4. So we will get this much deflecting torque for, you know, 1 milliampere, and that should be how much? How much did we get? 52.5 divided by 4. So it should be, you know, 52.5 divided by 4. It should be 13.125 micronewton meters. Okay. So that is the deflecting torque for 1 milliampere. Now we need to calculate deflection for 1 milliampere. This is deflecting torque. So how to calculate deflection? So this torque, you know, what should be the mm, expression of deflection? That is related to a spring, right? So a spring will deflect how much torque is being applied on the pointer. So since torque is 13.125, let me write torque is equal to k theta. So torque is this much. K we know. K is mentioned in the question. How much is the K? It was provided. It is 2.25 micronewton meter. So 2.25 micronewton meter per degree. Micronewton meter per degree. And bring, or carry units also along with your data or numerical value. Yeah. So 13.125 micronewton meter. This is K, and this will be theta. So theta will tell you the deflection in the pointer for 1 milliampere, and that should be 13.125 divided by 2.25, and it will come out to be how much? How much did you get? So let me divide it. 13.125 divided by 2.25. So it should be 5.83 degree per milliampere. I hope you must have also got the same value, and the answer range was provided Answer range was 5.542 to 6.125 degree per milliampere, isn't it? Any doubt in this problem? Okay, if not, then we will move to the next part, third part. So what was the third part or third question? The pointer stays at 0 degree when no current is passed, and 0 degree corresponding to 0 ampere, okay, and 100 degree corresponding to, full scale deflection. So we need to compute the full scale deflection. How to compute it? So mm, corresponding to, in the last problem, corresponding to how much? Yeah, corresponding to 5.83 degree, there was 1 milliampere. That is the, definition of sensitivity. So sensitivity, if it is provided in the question, if you find any question not in the similar fashion, and rather some sensitivity would be given, right? So do not bother about that, and you can solve it. So sensitivity is 5.83 degree per milliampere. Okay, and we have to go till 100 degree for full scale deflection. So the full scale deflection will be sensitivity divided by, sorry, 100. This a full scale deflection will be sensitivity divided by, current. So 100 degree divided by 5.83 degree milliampere. So that would be your FSD, isn't it? And FSD in milliampere, how much it will be?
17.1.
17.1 milliampere, and that is well lie within the range. So range was 16.29 to 18. So I guess you must have solved it. Okay. So any doubt regarding this problem? If
No,
not,
sir.
then next. Okay, great. So if not, then the next problem is very interesting, and someone was asking related to this problem on the first session, isn't it? So who are that? I cannot remember. That problem related to, so fourth problem states that critically damped oscillation when external resistance is 125. Okay. So we need to find the critical damping constant in nanonewton meter per degree per second. So we need to find K, or let us say, not confuse it with K. Why is it lagging? Uh, so yeah, so this AD current damping expression also we derived that day. That was how much? BAN square by, R external plus R coil into what was that? Do you recall from the first lecture? So damping torque was dependent on which factor? Related to position, velocity, inertia. Three terms were there, right? We derived that day. So if you do not recall, it was related to, position. So d theta by dt. Okay. And this much is the damping constant. We discussed this expression in very lengthy detail. So I hope you must have solved it. So this is the constant, BA in square divided by R external plus R square, and all of the parameters were given. So A will be equal to, okay, let me shift to this. Yeah. So K will be equal to BAN square divided by R square plus R external. Okay, B was given in this problem. How much? 0.7 into area. We also know 1.25 into 1.5 into 10 raised to power minus 4, because all of them in centimeter and number of turns is 100, divided by R square is 175 plus R external is given in this part, that is 125 ohm, isn't it? How much it will come? That will be your damping constant. And you will also need to take care of the unit. That should be nano Newton meter per degree per second. Okay, so you will have to sideways the 10 raised to power minus 9. Okay, so if you compute, or if you may have computed, let me compute it for you. So it is 0.7 into 1.25 into 1.5 into 1.3125 to 1.72 divided by 200 into 10 to the power minus 8. 17.2 divided by 10 to the power minus 8. If we have to side it, oh, no, 1.7 into 1.25 into 1.5. Okay, this would be 10 for minus 4. Hmm. Be 1.7. Two two six 1.7226 into 10 for minus 8. 17. Yeah. divided by 300, 57, 7. So there's some mistake here. How much did you guys got for this question?
Zero point 0.057 into 10 to the power minus
Sorry, how much? 0 point something you are saying?
0.057 into 10 to the power minus 9.
0.057 into 10 raised to power minus. Yeah. So this much you got with the same calculation which I just did, or did you calculate it separately for your, or did you use some? Okay, 1.73 into 10 raised to power minus 11. It means 173. It is right. Hmm. So your answer must have come as wrong, right? If you have submitted the assignment, isn't it?
Yes.
Yeah. I don't know why such a range is given. Range may be wrong because this is the expression for calculating damping. Let me recheck once last time. Hmm. Okay. 7 into 1.25 into 1.5. So 131.25 into 10 raised to power minus 4 square divided by 300. Okay. Now this should be 131.25 17,226.5 into 10 raised to power minus 8 divided by 300. Hmm. Same calculation divided by 300, it is 57.5, 57.4 into 10 raised to power minus 8. Hmm. So it should be 574 into 10 raised to power minus 9. And that is not the range. So maybe it is wrong. So we can, or you can post this in the discussion form. So we can see that if some mistake is done in this range. Okay. So this much is nano. No, this much is not nano. This will be Newton meter per degree per second. And answer should be 574 nano Newton meter per degree per second. So some of the answers you have been getting 574. Yeah, Siva has got the same answer 574 nanonewton meter per degree, but that is not the range was provided by NPTEL, right? So that's an issue. So we can discuss in the discussion form. So you can post there and we can continue our discussion there. those whoever are responsible to provide answers, they will take care of this thing. So anyone is getting the answer which is coming in the answer range? I don't think so, because that range is not reasonable, isn't it? Yeah. NS is also getting the same 574 nanonewton meter per degree per second. Yes. So please do not hesitate to post on the forum. Okay. So this is the way by which we should solve this problem. Okay. So this should be the answer, and we have discussed this in lengthy detail. Anyway, we should move to the next question, that is fifth one. We need to calculate the shunt resistance to convert this PMMC instrument into an ammeter of range 0 to 100 milliampere. So this must be very easy. So PMMC to ammeter of 0 to 100 milliampere. Right. So right now its full scale deflection is how much? We just now calculated its full scale deflection. How much did we calculate it? Let's see. Yeah, so full scale deflecting current, we calculated that was 17.1 milliampere, right? So FST is 17.1 milliampere, corresponding to 100 degree, isn't it? Now, a full scale current is this much, which means this PMMC can go up to 17.1 milliampere, and we have to convert it with an emitter of range 0 to 100 milliampere. So peak current should be 100 milliampere. So simply this much current in this branch, we have to connect a shunt resistance, isn't it? GMMC, so that this whenever 17.1 milliampere should flow here it should be 100 milliampere, and rest should flow into the shunt branch. So here it should flow 100 minus 17.1. So it will be 82.9 milliampere. Okay. And PMMC resistance was mentioned in the problem. Okay. So at that time, when PMMC resistance, we will also have to consider. So that 17.1 milliampere into PMMC resistance, that was 100 ohm, that is provided in the first statement, because this was the question from that statement. So voltage we can calculate directly, 17.1 into 10 to the power minus 3 into 100. So it is straightforward calculation. It should be 1.71 volt, right? And it should be this much current, 82.9 milliampere into RSH. So how much will be RSH here? 1.71 divided by 82.9. So how much will it come? Milliamperes into 10 to the power minus. 1710 divided by 82.9. So how much will it come? 1710 divided by 82.9. So this much is coming, 20.62, isn't it? Hmm.
Yes.
And that is not again in the range, is it? No, that is again not in the range. Anyone got the different answer for this? Oh, 17.1 milliampere. Okay. So you are saying 17.1 milliampere was flowing. That was full scale difference. Okay, so 20.6 milliamperes CY is also getting. So we can discuss this solution also in the discussion form. I don't know how so much errors are coming, but still, so we have to focus on methods as of now, or we can calibrate if there are some errors, but this is kind of way to solve this kind of problems. Anyway, let's move on. So now the important part, we have to, I don't think here any answer would be wrong. So we needed to correct, we needed to select the correct statement. So this emitter will exhibit under damped response, over damped response, or either under damped or over damped, depending on the external circuit. So since shunt resistance is 20.69, okay, and critical resistance, total critical resistance was how much? R critical was 175 plus 125, isn't it? So it was 300. So, and I also straight away noted down a couple of points during first lecture. If R is less than R critical, it will give which condition? R equivalent will be less than R critical. Which condition will the system or this emitter will exhibit? It will exhibit over damped oscillation. Okay. And vice versa. If it is higher than R critical, it will under damp. And how will we calculate R equivalent? R shunt parallel with R emitter, isn't it? If you calculate equivalent resistance of this circuit, how much they will come? Which is nothing but 82.9 is in parallel with 100 ohm. So it will be, lower than the least value. So it will be anywhere less than 82.9 if you calculate. Okay. And this R equivalent is less than 82.9, which is less than 300 ohm. So which leads to the statement, it is overdamped, isn't it? So the statement B will be correct. So the above emitter will exhibit overdamped response. Any doubt here? Okay. So the next part related to voltmeter, we calculated or we solved such kind of problems in lecture 1. So now we need to convert this PMMC with voltmeter of 0 to 25 volt. Okay. So for voltmeter, we need to connect a series resistance. Okay. So this square resistance is 100 ohm. This R series. Okay. And this full scale deflecting current was 18. How much was it? 17.1 milliampere. So 17.1 milliampere is this current. So now, the total resistance would be 25 volt now, isn't it? Earlier, how much it was? Without connecting any series resistance, earlier this voltage was 17.1 milliampere into 100 ohm. So it is nothing but 1.7 volt. So basically, we are converting a PMMC with full scale deflecting voltage of 1.71 volt to 25 volt. For that, we connected one series resistance. Now, this drop across this resistance would be how much? 25 minus 1.71 volt, isn't it? So that much should be there. So now we can easily calculate this series resistance. Okay, that is 25 minus 1.71 divided by 17.1 milliamp, and it should be how much? 25 minus 1.7 divided by 17.1. So 1362 ohm, or close to that. So, okay, 125 minus 1 divided by 1361.9. So 1362. Okay. So how much are you guys getting here? Are we sure we are not committing any mistake? Because 17.1 milliampere is the full scale. 1.36. 1.36 kilo ohm, right? 1.36 kilo ohm. And again, the range is given wrong. So this 17.1 milliampere is full scale deflection. Is it correct? Let me verify it first. Full scale deflecting current is correct. Yeah, full scale deflection current is 17.1 milliampere, and coil resistance is oh, oh. Coil resistance is 175 ohm. I took 100 ohm. It should be 175 ohm. Oh, that's this resistance is 175 ohm. That's why so many solutions could not be wrong. Right. So now, did you got the error? Where was the mistake committed from my side? I took 100 ohm corresponding to 175 ohm. That is why errors were coming. So now this new voltage here should be 17.1 into 175. It is 2.99 volts. So now it should be 25 minus 2.9. 25 minus 2.99. Yeah, so now it is coming as 1287.1. So now it should fall within the range. Yeah, so now it is falling in the range. So range is nothing but 1219 to 1348. So I hope you didn't commit this same mistake during the submission of the assignment, right? 175 ohm is here, and I hope the last problem will also have the same mistake. Yeah, here. So here 175 resistance, and it should be this much 175. And 75 into 17.1, 2.9 volt. 2.99 volt. And now our state should be 2.99 So 36 ohm is coming as answer for that shunt resistance of a meter. And how much was the range? So range was also correct for this question. That was 34.4 to 38.02. So this is also correct. Any other question had any mistake? No, this problem still has the wrong answer, I believe, because here we considered 175 only. So I don't think this question has the correct answer. This one was fourth. So fourth question still have we still have doubt related to this fourth problem. But all other answers for a meter and voltmeter is correct. So please make sure that the yes 36 ohm. Okay, so let us any doubt here. I know some confusion is there, was there. We can solve this confusion before moving on if you want. So just, and how much did you submit? Have you submitted NS? Did you submit all these assignments? Okay, great. So I hope you submitted 36 ohm. Okay, great. So now we have calculated this series resistance. Now we have to find out whether this system will be overdamped or underdamped. So what is the answer? Just by looking this circuit or looking this answer, you can tell me what will be the characteristics of system. Yeah, Niranjan. Yeah, you have also submitted. Okay, great. So please let me know quickly what is the characteristics of this voltmeter. Underdamped, overdamped, critically damped. Underdamped. That's excellent. Underdamped. So why is it underdamped? Because just now I told this R equivalent is R critical. And from where I am getting this value of R critical? I am getting this value of R critical from the first question where it was mentioned that system will exhibit critically characteristics when the total resistance is 300 ohm. And here our equivalent is in this voltmeter circuit 1287.1 plus 175. So it is definitely higher than 300 ohms. So that is why it will have. Yeah. So if there is no doubt, we can move on to the next part. Okay. Yeah. So the next question is related to electrodynamic ammeter. I hope you must have solved it. Ninth question. So from ninth question, we have been given with mutual inductance is how much 500 sine theta minus 5 microhenry, where theta is the deflection of the moving coil in radian. Now a spring constant is also given 0.15. My doubt that was my doubt. Option C, if external resistance changes, it can change. Yes, definitely. This nature definitely can change if external resistance. Okay, so you asked that question, NS. Right. So that's very good question. So if external resistance changes, definitely this all characteristics will change. Right. So yeah, I hope you got it. Hmm. So K is given, the spring constant is 0.15 micronewton meter per degree. And we need to find out the deflecting torque when deflection is equal to 50 degree or is equal to 5 pi by 18 rad. Okay, so it's pretty simple, isn't it? What to do? Just we know the expression of torque in electrodynamometer ammeter, right? And it is non-linear also. So it's definitely I square dm by d theta. Okay. And it's which expression will you use rather? Because you do not know the current value. So I square dm by d theta is not feasible expression for this part, which I also discussed in first lecture, right? So the feasible expression to calculate it is nothing but k theta, and k is 0.15 into 10 to the power minus 6 into theta is 5 pi by 18. We need to consider 5 pi by 18 or 50 degree. What to consider here? Either we can select 5 pi by 18 radian or we can select 50 degree. What will we have to select? You'll have to let me know. Otherwise, if you select wrong unit, then your answer is gonna be very wrong. So you'll have to be careful here, and you'll have to look at the unit of K. In what unit K has been provided in this question. So K has been provided in terms of degree. So you'll have to consider 50 degree, isn't it? So the solution should be 750, 1.5, 7.5, 7.5 micronewton meter, isn't it? I hope you are getting this answer within the range 7.5 micronewton meter. Okay. Now, any doubt in this part? Previous question, so option C is also correct. Ah, oh, I didn't see option C. The above voltmeter may exhibit either response depending on the external circuit. Okay, okay, yes, yes, definitely. It could be true. This statement seems absolutely correct because as external circuit will change, external circuit resistance will change, and this may come down, less than the total resistance of voltmeter. So it should be considered. So which option did you select? Because they have apparently given more priority to option A. Hmm. Yeah, that's very confusing part. I selected A. That's good for you because you will get marks for that. But option C is absolutely correct. It could be absolutely correct. Hmm. Depending on external circuit, definitely. Yeah, we'll have to discuss this in the discussion forum, right? So those who have marked C or A, we can discuss it on discussion forum because of course if it is not a multiple choice question because it was single choice question, right? So if there is multiple choice question, then option A and option C both should be correct. 60, yeah, Niranjan, 60. C could, C could be correct, you know. A is correct for sure because they are asking for this system. So A is definitely correct and C could be correct. So it's a bit confusing option. Yeah, I didn't pay attention to that option. Yeah, C could be correct for both 8 and 6. No, no, no. For 6, it will not be correct because the least resistance was, 82.9. So for 6, it will not be, it will not hold true because one resistance is 82.9 ohm. So no matter how resistance you increase, no matter how much resistance you increase here, it doesn't matter. Oh, sorry. External resistance is, uh, okay, this is not 100. This is 175. And R shunt we calculated 36 ohm, right? So 36. We didn't update it. 36. So 36 one resistance is already there, shunt resistance. Okay. And emitter resistance is 175 ohm. So no matter how much either of the resistance you can increase, basically you can increase shunt resistance only because emitter resistance is fixed. So if you increase 36 or 175, the equivalent resistance will be lower than the least resistance. So that should be less than 36 ohm. So it will never cross the limit. But on the other hand, for the voltmeter, it could cross the limit, right? Let me think. Uh, okay. If externals, yeah, if external resistance, let me write it. If R external is R external is 5,000. If R external is 5,000, then total equivalent resistance will be 5,000 plus 175 ohm. 175 ohm. So let me think here. This will be R equivalent, or if R external is, oh, okay. This is one condition. Okay, this is the one condition on higher side. On lower side, if R external is 25 ohm, so R equivalent will be 175 plus 25, so it will be 200 ohm, isn't it? And this voltmeter resistance is equal to this voltmeter resistance is equal to 1287 plus 175. 1287.1 plus 175, 1462.1. So this much 1462.1, okay, it, this is the equivalent resistance, and 1462.1 is higher than 200 and less than 517. Hmm. Now you got why option C will not be correct, because critical resistance, you know, critical resistance is anyway, it is fixed at 300 ohm. Okay, okay. So now listen carefully. So critical resistance is kept at 300 ohm, and this voltmeter resistance is not going to change from 1462.1. Okay, no matter what external resistance is, okay, critical resistance is not going to change. Are you getting my point? Critical resistance is not going to change for this system, no matter how much external resistance you connect. Okay, so for this voltmeter, this much resistance 1462.1 is always higher than 300 ohm. Okay, so that is why it will exhibit only under damped oscillation. So let's say if you connect of RX of 25 ohm, so you connected external resistance of 25 ohm. So what will happen? R equivalent would come out to be 200 ohm, but that would be different circuit for this question. For question which one? For question 7, this voltmeter with range of 25 volt, this much resistance is required. You cannot change this value, no matter how much you have increased the external resistance. Your critical resistance will be same, and your this equivalent resistance will be same. So that concludes that is independent of the external circuit. So I hope now you got. If you are still confused, I can again clear it or clarify it further, but it will have no role. The external resistance will have no role in deciding the oscillation. because critical resistance is already fixed for this voltmeter. So I hope, Niranjan, am I clear? So option A will only be correct. Yeah, so NS, that was really a very good question you asked. Yeah, yeah, great. So it's better to commit mistakes here in assignments rather than jam or anywhere else. So no need to be disheartened. Okay, Niranjan? Okay, now move on to the next problem. Yeah, so we were solving this problem. So in ninth, we got the answer of 7.5 Newton micronewton meter. So that is coming within the range, isn't it? Okay. So let's move towards the next problem. So now in 10th part, we need to we need to find current when deflection is 50 degree or 5 by 18 rating. So again, we got the torque that is 7.5 into 10 to the power minus 6 is equal to square dm by d theta. So for that, we need to calculate dm by d theta corresponding to theta is equal to what? Theta is equal to 5 pi by 18. So it will come out to be 500 cos theta minus 5 by 9. And theta is nothing but 5 pi by 18 minus 5 by 9 into 10 to the power minus 6. So which will nothing will be 500 cos 5 pi by 18 minus 5 into 5 by 18. So 3 pi by 18 into 10 to the power minus 6. 500 cos 5 by 6 minus 6, 500 cos 30 root 3 by 2. So this is the dm by d theta. We calculate I square, which is nothing but 7.5 divided by 500 into root 3 by 2. Okay. So how much it will come out? Oh, 36.5. Okay. So how much will it come out? Under root of 0.0173. Let me use the calculator. 0.0173. So 13.15. So it is 13.15. Okay. Oh. 0.1315. So, and we have to provide the answer in milliamperes, so it will be 1315. So I hope you are getting the answer in the range. 0.13, yeah, 0.13 ampere, but question was asked in terms of milliampere. Yeah, 0.1315 is correct, but question was asked in terms of milliampere. So you need to provide in terms of milliampere. So I hope you have done that. Okay, so that was the second subsection. Now the third and final subsection of data assignment. Any doubt in this part? Let me turn on the light. Okay. No, sir. Okay, great. Thanks. So let us move to the third subsection quickly and all second subsection. Yeah, third questions. Now, electrostatic, and we already know, we have already learned that electrostatic instrument is used to measure voltage, isn't it? So now question 11. Here are two semicircular conductor plates. Okay. One is fixed and other will rotate parallel to the fixed plate such that overlapping area between them can change. So radius of the plate is 5.5 centimeter and distance between plates is 7 millimeter. A spring constant is 0.15 micronewton meter per degree. Okay. Now we need to compute deflecting torque when 1.6 kV voltage is applied between plates. Okay. So what will be the expression of deflecting torque? We have discussed already. What is the expression? I hope you recall. Half into V square into dc by dt. Isn't it? V is given. C, capacitance. Capacitance expression is nothing but A which was the function of theta, and I discussed that in great detail, that how theta we will have to consider. So A which varies with theta and epsilon divided by D. Okay. Now, so epsilon we already know, 8.85 into 10 to the power minus 12. D is 7 mm. Okay. Now, dc by d theta. So first we need to find out C. So dc by d theta. So C we have calculated. A theta will be how much? In last lecture we discussed that one semicircular plate is placed like that, and this is the theta is equal to 0 degree, isn't it? And another semicircular plate is here. Okay, so it can rotate till, you know, if it comes at this axis. So this axis is theta is equal to 90 degree. So still there will be, you know, overlapping area. So when overlapping area ends, when this semicircle reaches at this position. Sorry. And this axis is theta is equal to 180 degree. So theta will have to consider 180 degree, isn't it? So a theta will be nothing but pi r square by 2, that is the area of semicircle, into theta divided by how much? Pi. Why pi? Because pi, this parameter is related to this limit. So as soon as it reaches the axis of 180 degree, the overlapping area will be 0. No, sir, 90. What did I taught in that lecture 2? Lecture 2. Yeah. So you recall this lecture. So theta was 90 degree for, you know, 1/4 of the circle, but it was 180 degree or pi for semicircle, isn't it? Are you getting that truth? Should I explain it again? This lecture, if you can recall, here I clearly explained that theta. uh, Here I clearly explained that theta will be 180 degree. How and how also I explained for semicircle and for 1/4 of the circle. Okay, Niranjan, yeah, great. I hope everyone agrees with that. So theta will be 180 degrees. So go and revisit the last lecture where that is why I very much emphasize on this part, because this will be very tricky once the portion of circle will change. So you draw it. That is why you draw it on any rough paper. That at what axis this uh, you know overlapping area is getting 0. Till that axis, you will have to consider this value of theta. Okay. Yeah. So now theta is pi. So the a theta is nothing but pi r square divided by 2 pi into theta. So we can plug in this value here. Here, isn't it? So C will be, capacitor will be, oh sorry, dc by d theta. So this is a theta. So C will be equal to pi r square by 2 pi into theta into epsilon by d. So dc by d theta is equal to how much? Theta will just disappear from here, from this expression, and pi will also get cancelled out. So r square by 2 into epsilon by d. So this is the dc by d theta for this form. Okay. I hope there is no doubt till now. So now the value of torque. So V square by 2 dc by d theta. V is mentioned in the problem. How much? V is 1.6 kV, isn't it? V is 1.6 kV. It means 1600 square by 2. dc by d theta is r square by 2, r square epsilon by 2d. So radius is how much? Radius of each plate is 5.5 centimeters. 5.5 into 10 raised to power minus 2 square. Epsilon 8.85 into 10 raised to power minus 12 divided by 2 into the distance between the parallel plates are also given, that is 7 mm. Okay, so you'll have to calculate this now, and torque is being asked in terms of you know, micronewton meters. So you'll have to consider -6 here. So how much will it come out? So 1.6. Okay, let me calculate it. 1.6 square into 10 raised to power 6 into 5.5 square into 10 raised to power -4 into 8.85 into 10 raised to power -12 divided by 14 into 10 raised to power -3. Okay, so I'll 6, 12, 16 plus 16. I'll just rough out the square. 16 minus 16 plus 9. So it will be 7 minus 7. So whatever will come out, 1.6 into 5.5 square into 8.85 divided by 14 into 10 raised to power -7. Okay, so this we will have to calculate. So 1.6 into 5.5 square into 8.85 divided by 14 48.95 to 4.8 divided by 2. Yeah, this 2 we have left here. This 2 also will come here. So 4.85 divided by 2. So 4.895 divided by 2, it is nothing but 2.447 micronewton meter. So I hope you are getting the same value, 2.447. Let me see whether this lie in the range. Yeah, so range is still from 2.326 to 2.571. So this was the range and it will lie in the range. Are you getting the same value? I hope so. Okay. Any doubt in this question? So calculation is a very, careful part of solving any problem, because no matter how much concept you know, no matter how much, depth you have gone, but your calculations could be precise. Otherwise, you can lose significant chunk of marks in the exam. So while submitting any assignment, any further assignment also, please carefully recheck, re-verify multiple times your values so that your all hard work should not go in the vain. Okay, so I hope there is no any doubt in this part. So let us move to the last question of the assignment one. That was, we needed to calculate the deflection theta. Okay, if 1.6 kV voltage is applied. So how to calculate theta? We have torque, we have a spring constant, so we can calculate theta. So torque we have calculated, that was, or that is 2.447 micronewton meter. So torque is equal to K theta, 2.447 micronewton meter. K is given as 0.15 micronewton meter per degree into theta. So theta will be equal to 2.447 divided by 0.1. So it is nothing but 16.31 degrees. I hope it was pretty much simple problem. Yeah, and range is also 15.51 to 17.14 degrees. Okay, so I hope you are getting the answer for this part as well. So any issue in assignment one, only question number 4. So you will have to discuss on the discuss number 4. Okay, so what we are getting for question number 4, the answer is 557 we are getting. Isn't it? We are getting how much? 557. Oh no, 574. 574 nanometer. Sorry, yeah, nanometer degree, nanometer Newton, meter per degree, and the range is given as both question range is given from 9.52 to 10.52. So we'll have to discuss this. You re-verify at your own end once more after this lecture, and please post this question on the discussion forum. Okay, any doubt from assignment 1? The next topic we can start ohm meter where we left in last lecture. If not, okay. So I hope you are able to recall in last lecture we concluded something, right? What was the conclusion? Two statements I wrote in last lecture. At the very end of the session, I wrote for any ohm meter to work perfectly, Rx should be equal to R internal. And this was the first point. And second point was, what was the second point? Where to maintain the pointer? Rightmost, leftmost, or center? So maintain the point at center, near the center. Maintain the pointer reading near the center point. Okay. So these both points we concluded the last lecture with. So let's move ahead and we can have some questions. So before that, we'll have no. So basically, for any circuit, there are multiple configurations how we connect voltmeter and ammeter. So basically, ohm meter is nothing but the measurement of voltmeter and ammeter, you can say in other words. So let's say you have a resistance here, which is Rx, and you want to measure this resistance. So what will you do? You will just apply, let's say it is connected to supply. Okay. So what will you do? You will connect a voltmeter here. Okay. And you will connect an ammeter here. Okay. Okay. And the reading of voltmeter and ammeter. So Rx will be nothing but voltmeter reading divided by ammeter reading. But this is not the ideal. This is not the ideal calculation. Can you please teach the model assignment of week 3? Model assignment of week 3. Let me see. Okay, okay. So its due date is very soon, that is 14th August. Hmm. Unfortunately, we cannot go with this. Hmm. So actually, we are right now in ohm meter only. So week 3, I think we will be able to discuss next week only. So today the plan was to discuss assignment 1 and you know discuss the concepts and questions of week 2. So is any other lectures? Did they discuss about assignment model questions of assignment 3? You must see the recording of theirs because I did not plan about week 3 today. So I hope it should be okay. They must have discussed. Otherwise, you should let me know, in the one lecture before what to discuss, or otherwise you can send a mail to discuss it because it will be bit out of synchronism if we leave this topic here. Okay. Okay. So yeah. So this okay. Thanks. So this the distance will be voltmeter reading by ammeter reading, and this is not always ideal. The reason behind it is if there are some circuit which is dependent on the equivalent resistance. If let's say this Rx is not very straightforward, so if we'll have some connection of alternate way, let's say there are two possibilities to connect any resistance. So either you connect ammeter before the voltmeter. So this is configuration 1. This is configuration 2. So what will you choose and when will you have to choose among both these circuits? So there are conditions, okay, and there are regions behind the selection of the circuit, when to go with this configuration 1 and when to go with configuration 2. So I'm writing it. Configuration 1 is suitable when Rx is much higher than ammeter resistance. Okay. And configuration 2 is suitable when Rx is much less than voltmeter resistance. Okay, so these are two conditions. When uh, based on that, we'll have to select the configuration. Why? The reason behind it, because here, if you measure Rx, right, so that will be ammeter current and voltmeter voltage. But this current is same as ammeter, isn't it? But voltage is not same as the voltage across the Rx. So in configuration one, let me select. So in configuration one, you know, voltmeter reading will be what? Reading will not be equal to the voltage of Rx Vx. Voltmeter reading will be higher than this Vx or less than this Vx. You'll have to let me know. Is voltmeter reading is higher than Vx or lower than Vx by just seeing this circuit, by just seeing this configuration. It will be higher than Vx. Why? Because higher, right? Correct. Excellent. So it will be higher than Vx. Why? Because ammeter also have some resistance, isn't it? And some drop will be here as well because Ia is same. So Ra. So the voltmeter reading will be nothing but Va plus Vx. Okay. So that is why it will be higher. Okay. And in this configuration, it is desirable to have Rx is much higher than Ra. Why? So that this Va, so that Vx is much higher than Va. So that this drop across the ammeter should not impact this circuit or should not impact the reading of our ohm meter. Right? So error should be minimized, isn't it? So what will be error? So error will be here. If you calculate error, it will be estimated Rx. Estimated Rx means whatever we are going to calculate, right? So that will be means what is actual minus desirable, okay, divided by desirable, isn't it? So this will be your error into 100% if you are going to compute in percentage. So what is actual? Actually nothing but Rx plus Ra. Okay, this much will, what do you mean by actual resistance? That will be that will be shown or that will be displayed over your instrument. So whatever you are going to get while measuring, this much is the actual. Minus desirable is what? The instrument should only reflect Rx value, isn't it? And divided by desirable is again Rx. So it will be Ra by Rx into 100%. So the lower the value of Ra is, the error will be lower. So it is desirable to keep the value of RA as low as possible so that you can use this configuration. When the resistance of emitter will be larger or comparable to RA or significant, then your error will be higher. Okay. And in case if RA is equal to Rx, then what will happen? If RA is equal to Rx, then error will be 100%. Okay. So it will show you double the resistance. Of course, it will show double because RA is equal to Rx. Okay. I hope there is no doubt in this. Now coming back to the second configuration. Okay. So what about this configuration? We said about this configuration that Rx should be much less than RV. Why? Or RV should be no, or RV should be much higher than Rx. Why? Could you please let me know the reason behind it? Hmm? To prevent current flowing into voltmeter. Exactly. Excellent. NS. So see, when RV is higher than Rx, then whatever ammeter will read the current IA, okay, almost all of them should flow across the Rx so that the current flowing through the voltmeter should be close to zero. Okay, so that is why IV should be close to zero. And to make that happen, you'll have to make RV much larger, close to infinity. Okay, so now you can see again we'll compute the error. The true resistance will be Rx parallel with RV, okay, minus desirable is Rx and divided by Rx into 100%. Okay, so Rx into RV divided by Rx plus RV minus Rx divided by Rx, isn't it? So it will be Rx RV minus Rx square minus RV Rx divided by Rx into Rx plus RV into 100%. So these terms will cancel out. So we'll have, and this also will cancel out. So minus Rx divided by RV plus Rx into 100%. Isn't it? So now the more RV you can see, if you increase the RV, your error is going to reduce. And negative sign just indicates that your error is error is showing, which means voltage is showing less than whatever is required or whatever is the actual resistance. That is only the negative sign signifies here. I hope you got it. Any doubt in this? So you have to keep both configurations in your mind, that when to connect those configurations. Okay. Now, the last topic related to measurement of AC quantity with PMMC. So we know that PMMC only measures DC quantity, but what happens if we use PMMC for AC quantity? So if you use PMMC, I hope no doubt related to this error related to both configurations for ohm meter. We'll solve some problems based on these topics. Okay. Or basically, first let us solve one question based on it. So here is the first question. Let me copy the question. So this is the circuit given. Okay. So here three circuit configurations are mentioned. We need to find all the resistance and RL. And the readings we circuits are mentioned. So I hope now we can easily find it. So how to do that? It's very easy and we can do it quickly. So we will have to start from the circuit 3, because here we can easily compute voltage and current are given, and this RA and RV, let me draw. RA will have one resistance, RV will have one resistance, isn't it? So you'll just have to do what? You just have to compute the RV here, and RV will be nothing but whatever the current is flowing through this ammeter, okay, the same current will flow through the voltmeter. Okay. So now RV will have voltmeter reading divided by ammeter reading. So it will be 200 divided by 0.2. I'm taking these values for circuit 3, ammeter reading and voltmeter reading. Voltmeter reading is the voltage across its own resistance, right? So that is 200 volts. So you'll get RV is equal to 1000 volts, 1000 ohm. Okay. I hope it is pretty much simple. for calculating RV. Okay. Now, if we know RV, now what can we do? We know this current IA. Okay. And if we know the equivalent resistance RV and RX in parallel, so whatever the current is flowing through the ammeter, the same current will flow among both of them. And since voltmeter is connected here, this voltmeter will be the voltage across Rx and Rv. So voltage will be same and current will be same. Only equivalent resistance will change, isn't it? So do not get confused and please stop me if you're getting any doubt here. So here for circuit 2, voltmeter reading by ammeter reading will give you what? RV parallel to Rx. Any doubt here in this statement? Why I am saying this? Voltmeter reading by ammeter reading will give you RV parallel to Rx. RA I am not considering in this particular circuit 2. I hope it is fine with you, right? Okay. So yeah. So now we just need to compute RV parallel to Rx. So RV Rx RV plus Rx is equal to voltmeter reading for circuit 2 is 273 and 3 ampere. So you can see that how these voltmeter readings are changing as you are shifting the your placement of voltmeter and ammeter. So here 273 by 3. 273 by 3. RV we have already computed 1000. 1000 Rx divided percent. Yeah, 1000 Rx divided by 1000 plus Rx is equal to 273 by 3. So if you calculate Rx from this equation, okay, you will get this value as 100.1 ohm. So Rx you are getting 100.1 ohm. Okay. So this satisfies that Rx is of course less than RV. And when I discussed here, when Rx is less than RV, which configurations would have been there? This configuration. So in question also, this configuration is mentioned, isn't it? So that is why Rx is less than RV. Now, for third part, circuit 1 observation, when ammeter is towards the Rx, so now voltmeter reading and ammeter reading will give you voltage across RA and Rx and current through RA and Rx. So now for circuit 1, voltmeter reading by ammeter reading will be what? It will be from circuit 1, you can see it will be RA plus Rx, isn't it? Yeah. Circuit 1, RA plus Rx. So this array is given as Rx we just now calculated in last part 100.1 ohm, and Rx we can calculate from this expression. Why isn't it working? Yeah. So and voltmeter reading is given for circuit 1 is 420 volt, and ammeter reading is given as 421 plus Ra, and if you solve Ra, you will get how much? 105 minus 100.1. So you will get 4.89. Notice. So this will be the value of ammeter resistance. So if such type of problems you are given with, please proceed with the simplest circuit you can see. Okay, that would be easier to proceed with the different configurations like just we did here. So I hope you got the idea behind connection of voltmeter and ammeter, where and which convention, which configurations would be more beneficial and why. The reason behind those configurations is very important, isn't it? So this is all about ohm meter. Okay. So from next lecture, we will solve some more problem based on it, and we will also see, you know, calculation of AC voltage with PMMC. Unless you have some recommendation to discuss me in the next lecture, if you want something specific to be discussed in next lecture, please let me know now so that I'll be ready with that topic. Or otherwise, if you want to go in the same flow, that also I can. So time is up now. So that is all about today. And we can meet on next Tuesday with the topic. If you let me know now, or I'll go with this same flow. And if you are lagging behind, if you are thinking that I'm lagging in this session, so there is some other sessions also for this course. If you want to, you should also see if they are solving some solutions related to the current week assignment. Actually, I want to discuss and discuss the depth of all the topics so that your concept should not be weak. I also want to discuss theory, not just problem, and how to solve problems, right? So if you have any suggestions, recommendations, I am open to take it. Please let me know. So this is all from my side. Thank you very much, Niranjan. Thank you everyone for joining and being here patiently to see all the concepts and solving problems. So I hope it is this space is fine with all of you. Thank you very much. Have a good night. Bye bye. Thank you. Thank you very much. Thank you, NS. Good night, Niranjan. Good night, everybody. Good night.